أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم. In today's lecture we will discuss the Kirchhof laws and Stefan Boltzman law. These are actually the laws that are about the thermal radiations to measure the magnitude of thermal radiation and the dependence of thermal radiation on various factors. In previous several lectures we discussed the phenomena of transferring heat from one place to another place. So in that cases we discussed the heat conduction process, the heat convection process, and the thermal radiation. All these three methods were used to transfer a heat from one place to another place. In the conduction process, some conductor was used to transfer heat from one place to another place without the transferring of mass. Only heat was transferred without the transferring of mass. In the case of convection process, heat was also transferred along with the transfer of mass. That was specifically used in fluids, in gases and in liquids. And the thermal radiation, what we discussed in the last lecture, is the way by which we can transfer heat from one place to another place with the help of radiations. Thermal radiation is actually electromagnetic radiations, especially in the infrared and visible spectrum, visible region. So that transfer heat from one place to another place. And definitely for the thermal radiation we don't need any medium to transfer it from any medium. But for the other two type of radiation, heat conduction and heat convection process, definitely we need a medium. In that case we don't need any medium, and that is why heat is transferred from sun to the earth with the help of thermal radiations. So we have the objective of understanding the Kirchhof law in this lecture, and later on we will also develop the Stefan Boltzman law, that is the experimental data obtained by the variation of the relationship about the thermal radiation, and later on we need to calculate the value of the Stefan Boltzmann constant. So what we want to get from the thermal radiation, first we need to know the Kirchhof law, that is about the radiated heat. The radiant excitant of non-black body depends on the nature of this and surface and nature of the surface and temperature. In the previous lecture we discussed that the radiant excitant of a non-black body depends upon the temperature, the surface, the nature of the surface, and the nature of material. But if we consider the perfect black body, then in that case the radiant excitant only depends upon the temperature of that body. So if we consider a non-black body at temperature T with radiant excitant of R and emissivity epsilon is introduced into a cavity having interior wall at the same temperature T, so what happen? The irradiance is irradiance here is represented by H. So what happened? The radiant power absorbed per unit area will be equal to epsilon H, because H represents the irradiance of that particular sample, and radiant power emitted per unit area is represented by R. So in the non-equilibrium, then if we consider non-black body, so what happen? For that case, if we consider the equilibrium situation, when the radiation emitted by the body is equal to the radiation absorbed by the body, this is actually the equilibrium situation for our particular radiation emitter systems. When the radiation emitted by the body is equal to the radiation absorbed by the body, so this particular body will be in equilibrium situation, and in that case R will be equal to epsilon H, because R is the radiant power emitted per unit area and epsilon h is the radiant power absorbed per unit area. So these two things will become equal to each other to consider the equilibrium situation. So for the value of h is equal to radiant power of the black body, so h is equal to RBB, where RBB is the radiant power absorbed per unit area, the radiant power emitted per unit area for the black body. So what happened, we want to replace the value of h by RBB in the above equation, in this equation. So this equation will be modified as a very simple equation, that the radiant power R is equal to epsilon RBB, and this could be explained as the radiant power, the radiant accident, the radiant accident of any body at temperature is equal to a fraction of radiant accident of a black body at that temperature, this fraction being the emissivity at that temperature. So the above equation is called as a Kirchhof law. So this is really very simple statement, that the radiant accident of any body is equal to the radiant accident of the black body at the same temperature multiplied by the emissivity at that temperature. So this is this specific relationship. This is called as Kirchhof law. And the emissivity of a body is determined experimentally by measuring the radiant accident of a body and dividing it by the accident of a black body at the same temperature. How we can calculate the emissivity is very simple. If we consider even the above equation, this equation, so we can divide both sides by RBB. So RBB at this side will be cancelled, and we will have emissivity is equal to R divided by RBB. So physically it means that the emissivity of a body is equal to the radiant power of that body divided by radiant power of the black body at the same temperature. So we can easily get the emissivity of that body even from the experimental condition as well. So the gain or loss of internal energy of the body is equal to the difference between the energy of the thermal radiation which is absorbed and which is radiated, is called heat. If we can define heat with using the concept of the radiation, so how we can define it? It is actually, the definition is not very different from the definition what we use for the heat conduction process or heat convection process. In case of radiation, the gain or loss of internal energy of the body, that is equal to the difference between the energy of the thermal radiation which is absorbed and which is radiated, that is actually called as a heat. I mean, again, the temperature, there should be a temperature difference. There is no temperature difference, so there will be no heat loss or gain. So gain or loss of internal energy by radiation absorption will take place only, I mean, again the condition, only if there is a difference of temperature between a body and its surrounding. If the temperature difference is the temperature is same, then there is no gain or loss in this particular case. So here we can calculate the emissivity of a body. So emissivity is equal to emissivity of a body we need to calculate. If we consider another example, a cavity whose interior wall are maintained at temperature Tw, and another black if we consider another body and place inside the black body, but the body which we place inside the black body is a non-black body at temperature T, that is different from the wall's temperature, is placed inside the cavity, then if we represent H, that is actually radiance within the cavity, R is the radiant accident, E is the emissivity, epsilon is the emissivity. So what happened? Radiant power absorbed per unit area is equal to epsilon H, and radiant power emitted per unit area is equal to R. So in the current situation, the above two powers are not equal to each other, and the difference between them is the heat transfer by radiation per unit area, because another body is present inside it. So if we represent if we use the if we consider that dq is the amount of heat transferred in time dt to the non-black body whose area is A. So we can write this equation is equal to dq divided by dt is equal to A into epsilon h minus r, because if we consider the body to be an equilibrium situation, some of the heat radiated by the black body will be absorbed by the another non-black body that is present inside the body. So emissivity and excitant are the function of temperature. So if we consider emissivity and the excitance of a body, that are actually the function of temperature of the body, and irradiance H is a function of temperature of the walls of the another black body that is placed. So we have the equation for that R is equal to epsilon T, because the epsilon depends upon the T, emissivity depend upon T, and the radiant excitant depend upon the T as well, and H depends upon TW, I mean the temperature of the walls of the black body, RBB. So then we can modify the equation as the last equation could be modified if we use it, that dq divided by dt is equal to A epsilon into T into RBB TW minus RBB into T, and this equation specify that the rate at which the radiant power transfer, the rate at which the radiation transfer the heat is proportional to the difference between the radiant excitances of the black body at the two temperature. This is very simple thing or simple relationship what we had developed, that the rate at which the radiation transfer the heat from black body toward the non-black body is equal to, or it is proportional to, the difference between the radiant excitance of the black body and of the black body and at the two temperatures. So we have another relationship that has been developed to specify the black body and the variation between the black body and temperature. So that is developed by Stefan and Boltzmann. So that is why it's called as Stefan Boltzmann law. So stepwise experiment are been performed, and in 1987 Stefan concluded from that experiment. Actually he only get information from the experiment and then draw the information and develop the relationship between them without any theoretical background. So he found that the heat transfer between a body and its surrounding is proportional to the fourth power of the absolute temperature. So this was his so later on the Boltzmann provided theoretical understanding for the purely experimental data. So both theoretical understanding and experimental data are conformed to develop a rule for the relationship for the thermal radiation. So according to this, the heat transfer between a body and its surrounding is proportional to the fourth power of the absolute temperature, or in other words you can say the radial excitant of a black body at any temperature is given as a RBB, that depends upon the temperature, is equal to sigma T4, where sigma is called as the Stefan Boltzmann constant. Sigma is the Stefan Boltzmann constant, and this means the radial very simple, that radiant excitant of a black body at any temperature T is given as. Here if we look at this equation, there is no information regarding the surface area of the body, there is no information regarding the nature of the material of the body, but it is mentioned here that the radiant excitant of a black body only depends upon the temperature, and that is also confirmed by the Stefan from this experimental observation, later on theoretical background provided by the Boltzmann. So again we generalize the idea from this, that the radiant accident of a black body that only depends upon the temperature. But if we want to numerically measure the relationship, then it is proportional to the fourth power of temperature, or in other words you can say it is equal to the fourth power of temperature multiplied by the rate with the Stefan Boltzmann constant. So if we use the heat transfer by radiation between a body at temperature T and its walls at TW, how we can write using this Stefan law? dq divided by dt is equal to A epsilon sigma TW4 minus T4. So how to determine the Stefan constant? This is most important for us because the unknown quantity here in this equation is the Stefan constant. Radiant accident we need to know, and that could be easily calculated from the relationship with this with this black body and its temperature. So the only thing what we need to determine is the Stefan Boltzmann constant, and there are two methods utilized to calculate or to measure the magnitude of the Stefan Boltzmann constant. One is the non-equilibrium method and other is the equilibrium method, and both are utilized to measure to calculate the magnitude of the Stefan constant. First we need to discuss the non-equilibrium method, how we can do it. So we do some experimental procedure for it to measure the Stefan Boltzmann constant. So what we do here, a black and silver disc is placed in the center of a large blackened hemisphere. So the silver disc is covered and shielded from radiation until the copper hemisphere achieves the temperature of condensing steam. So this temperature is measured with the help of thermocouple. So what is done again? Then the disc is uncovered and its temperature T is measured as a function of T. So assuming silver disc to be a black body, so what happened? We have this equation dq is equal to dq divided by dt is equal to A epsilon sigma T temperature of the wall ki power 4 minus temperature of the wall temperature of the body power 4. So we can get that as we know normally that dq divided by dt is equal to Cp, or if we do the cross multiplication, that dq is equal to Cp dt in a power equation. So what will happen? We can get the equation as equal to Cp dt divided by small dt is equal to A sigma Tw power 4 minus T power 4, or if we can get the value from this equation for the sigma, then it will be equal to sigma Cp divided by A T power 4 T temperature of the wall power 4 minus temperature general temperature dt divided by capital dt, I means T temperature divided by small dt. So this is one of the way with the help of which we can determine the Stefan Boltzmann constant. So this is the value of the Stefan Boltzmann constant we can get from this equation. The other method is the equilibrium method. With the help of that we can measure the Stefan Boltzmann constant, and that is also very simple method. We need to do some experimental procedure for this method as well. So in this case a hollow blackened copper sphere is provided with an electric heater and thermocouple, and it is suspended inside a vessel whose walls are maintained at temperature Tw. So what happened? Electrical energy is provided at constant rate until the sphere achieves an equilibrium temperatures T, at which the rate of supply of energy is equal to the rate of emission of radiations. So I mean, when the two things become equal to rate of supply of energy and rate of emission of radiation become equal to each other, then the body will achieve the equilibrium situation. So considering the black body at equilibrium, what will happen? the radiant power emitted by the body should be equal to the radiant power absorbed by the body. Or in other words, we can say that the energy supplied, actually epsilon E is the energy supplied, the constant that is the energy supplied toward the body, and a sigma T power 4 minus T W power 4 is the radiant exited of that body. I mean, it is the amount of energy that is released or radiated by the body. So in case of equilibrium situation, both should be equal to each other. So how we can modify this equation? The equation could be modified as a sigma is equal to 1 over 4 pi r square T power 4 minus Tw power 4, and from this equation we can get the value of Stefan Boltzmann constant. Here r is the radius of the sphere, and the value of the Stefan Boltzmann constant with high accuracy that has been calculated up till now is sigma, I mean the value of sigma is equal to 5.67 multiplied by 10 power minus 8 W per meter square dot K4. So this is something about the Kirchhof law and Stefan Boltzmann constant. This is actually the end of this chapter, and in next chapter we will discuss about ideal cases and develop some relationship regarding the ideal cases, and even develop the equation of state for the ideal cases. So that will be actually the theme of the next lecture. Thank you very much for now.